Hi guys, and welcome to another video. Today we're going to talk about add coder regular contest, several problems from there. And I must say that from the very first problems that you solve on A or C, you feel the difference with ABC. Because like technically all the ratings, they are kind of shifted, I would say biased, because apparently not too many lower rated users participate in A or C, and therefore like the rating of this problem on Kenku is about 1500, but it is worth 500 points. So what I believe is a way more accurate estimate of the difficulty is the points that AdCoder awards for each problem. So like that would be problem E or F in the most recent ABCs. And the usual rating of problems E or F is around 1800. And it definitely feels more like 1800 rated. But because like most of the users that do participate in ARC, they are kind of able to solve this problem because they have more time and also less like simple problems to waste time on. And therefore the ratings on Kenku got a little bit lower than they should be, I think. So yeah. So maybe this is like, it's only 1500 rated, but it feels like expert level. So that's why this video is called this way. And I wanted to take a look at three problems. They are quite different in nature, but we'll see as we go. So this problem, it comes from the very recent ARC 124, problem C, LCM of GCDs. In this problem we have two bags, one red and one blue, and n card packs. So both bags are initially empty, and each card pack contains two cards. So like one has number AI written on it, and the second card in the pack has number BI. So what we do for each pack, we put one of the cards into the red bag and one of the cards into the blue bag, and in both bags we compute GCDs, and then our score is LCM of those GCDs, which is kind of confusing. Like, I believe you had never, like, if you heard anything about, like, classical optimization, then you probably never heard anything about that. It sounds a lot like combinatorial optimization. We have only 50 cards, which is a little bit too much for, like, exponential solution. But maybe not, as we all say. And all numbers are, like, just usual ints. Nothing special in the constraints here. And of course we want to maximize the score. So what I was thinking here, I was thinking like, okay, like I have no idea how to optimize LCM of GCDs directly. The only thing that I noticed from the constraints is like AIs are large, but there are not too many of them. So if you really want to, you may be able to factor all numbers in just like square root time. You'll be able to factor 100 numbers, no problem. So I was kind of thinking like, can we do something with like prime factorization, maybe something like that. But I wasn't able to come up with any sort of approach that's pivoted around prime factorization. So I decided to look like for something else in the problem. Like these constraints don't allow for anything like way too stupid. One stupid solution would be to just like try all combinations. Right? But that's 2 to the power 50, which clearly does not fit into the time limit. Another observation is a tricky one. So like, let's say we still consider card packs one by one, and we try like both add AI to the red back, BI to the blue back, and AI to the blue back, and BI to the red back. So one thing I noticed here, like in this naive solution, when you just try to all sort of all combinations, like once you put like around 10 or 20 cards in, the value, you don't necessarily care about all 12 or 20 cards, all their specific values. What you care about is the current GCD of each bag, right? Like imagine you already put like half of the packs, and it so happens that GCD in the red bag is like 2 or 3. So you surely don't care like about what specific numbers led to this GCD. You only care that it's 2, and that's it. And then I started to think about like, okay, maybe I can bound the number of different values for X in some way. And I realized like, well, X is a GCD of some numbers, so surely it's a divisor of like one of them. For example, it's a divisor of A0, let's say. And then Y is a divisor of B0, or I should say A1, B1. And here I thought like, oh, wait a second, like actually another quantity that is relatively small, even for like large numbers like this, is the number of divisors, of different divisors. Now, obviously one stupid bound is like square root, but in practice we know it, like the number of divisors is much closer to log, I believe. I'm not gonna say like the exact asymptotics because I don't know it, but like I reckon it's like at most like several thousands, maybe 1 or 2,000 for numbers up to 1 billion. And then I realized, wait a second, like actually if the number of possible values of X is small and Y is small, they are small enough for the number of possible values of like a tuple of X and Y is also small enough. So what I should do is I should like disregard the history and only store pairs X, Y that I can achieve. And then the number of such pairs is like, let's say 1 million. So what I do is like, I do kind of DP, but at each layer I'm guaranteed that I have at most 1 million different values, and I have like 50 layers. So that convinced me to try this approach, and this is what happened. So let me zoom in a little bit. Oh, that actually does not. Okay. I will go on this. So what happens is we create an ordered set of pairs, because that is just like pairs of X and Y that we can achieve. Initially it's 0, 0 because we'll take GCDs, and 0 is kind of a neutral element with respect to GCD. So like a GCD of 0 and any number X is just X. So what we do is we loop over all card decks. We say like, okay, well, we'll try to add, we have 2 options for each possible pair X, Y in the history. We have 2 options. We either add A to X and B to Y, or I should say take GCD of them, or add B to the red back and add A to the blue back. That's what happens. And my naive estimate is, well, like on the size of this set, as it will be like 2 times the size of this set. So in overall you could expect it to be 2 to the power of 50, but we already said that X is a divisor of A0 or A1, and Y is a divisor of B0 or B1. And both of which those numbers don't have too many divisors, so the total size of XY, you can actually come up with a much better bound on the size of XY. So yeah, this is what happens, and that's like basically it.
And you just like loop over all pairs and compute LCM and just check maximum directly. Yeah, notice how these values are not longs, but by specifying the template parameter of LCM, you don't need to cast them to longs individually, you can cast like that. I assume that is like a little bit more cleaner than multiplying by one long each of them. Another thing to notice is that, well, by default you cannot put pairs into hash tables in C++, which is probably going to change around like 2027 or 2030. But for those of you who don't want to wait until this time, until the next like several C++ standards, you can use a pair hasher. One option is, it's very naive, but one option you can do is something like that. So yeah, notice this is important that this has const in it and this has const reference in it, because like an ordered set expects this structure to have a method of given signature, including const qualifiers. So yeah, and this is also one way of combining hashes. You can come up with a smarter way. Potentially a smarter way would be to have like some random value here, but like generate it once over here and then use it all the time. Potentially that's like smarter, because it prevents like reverse engineering of this function. Yeah, but even with such a naive hasher, we get like runtime of 6 milliseconds, which was absurd to me at the first look, because if you remember the problem then, which we should see soon. If you remember the problem, the time limit was actually raised from 2 seconds to 4 seconds. It was very surprising to me. If you look at all tasks of this contest, you can see that only the problem C has such time limit. I have no idea why, to be honest. I actually looked at the editorial and it kind of says the same thing. If you go here, you will see that they just say like how many divisor of A1 and B1 and that's it. So it was like the expected solution, and it works in 6 milliseconds, and for some reason the time limit was raised. I'm not sure why. It does not sound like Python users would have any troubles with that. So I don't know. Maybe it's like if you use a bad hash function, then you get a lot of collisions, and they kind of did not want you to suffer from that, but whatever. Like, so yeah. So this is kind of a recurrent pattern that I see, that sometimes your complexity kind of depends on the number of different divisors, and it's important to realize that in reality it's better than square root. So you should not be afraid of such things, because if you use naive estimate of square root, then you will think that this will TLE, but it doesn't. So I would say that it's like much more closer to log, but the constant is larger. I don't know the exact asymptotics once again, fortunately. We can actually try to look it up. If I won't do it right now, but if I will do it like soon, then I will put the link in the description to like some more intelligent way of estimating the number of divisors. So after that, I went to solve this problem, which I found a little bit more involved in terms of code, but it has a very nice idea. Quite a simple one, also one somewhat generic. We'll talk about it in a second. But in this, but implementation side, it's a little bit more harder. Nothing unusual, but just like something that you should know. So in this problem, we're given two sequences, A of length n and B of length n. We want to make A equal to B. We can perform the following operations.
we have two elements, AI plus 1. So what happens is we first swap them, then we add one here, and we subtract one here, which may be not very clear, but like once you swapped, AI actually refers to this position, so that's what happens. And we want to do that in minimum number of operations, or specify that that's impossible. So here, like, first observations that you can make is that, well, it's definitely impossible if the sums don't add up, because this sum of all elements of the sequence is invariant with respect to this sort of operation. So yeah, that was like kind of a necessary condition for the sums to be equal, but it was not sufficient, as I realized after constructing several samples. So yeah, so something better is needed in this problem. And here I sort of, I was thinking like, what we can actually do, like what we can, there should be something like some observation, because if you can do such operations and there should be a simple way to express the results of several operations, because if there is not, like if the result like depends a lot on the order or some other things, then like the space of possible sequences that we can get from A is just too large. So yeah, I was thinking like there should be a simpler way to like classify the results, like what you can technically get, what you can't get. So then we will be able to quickly check if B fits this kind of a pattern. And what I realized is, if you have this expression and you try to swap with AI minus 1, then you will get AI plus 1 plus 2, and here you will get AI minus 1 minus 1. And it was at this moment that I realized, wait a second, like the elements kind of don't change. They gain or lose something based on how many positions they shift. So at this point I thought, like, oh, okay, so if I shift AI, so like the resultant sequence only depends on like which number you put where. So you sort of can have arbitrary permutation, and based on like how far away and in which direction each number shifted, it will gain or lose some plus ones or minus ones. So I realized that if I shift AI to the first position, it will gain that much. Or if indices are 0 based, then it will gain that much, which is quite convenient. So at this point I realized, like, okay, so B0 should be equal to one of such values, all right? And B1 should be equal to one of such values. Or alternatively, B1 plus 1 should be equal to one of such values. And what you get as a result of it is like a set AI plus I for all I should be equal as a set to the set of BI plus I. That is basically it. And at this point you kind of think, okay, so like for sure I can tell when it's possible, when it's not possible, but like how do I minimize the number of operations? What is actually the number of operations? Well, we already talked about like how this process results in an arbitrary permutation of AIs. So, and like what is the number of moves? It's like number of inversions, right? If you write down the original indices, it was I minus 1, I plus 1. So 0 inversions here. Then you write the results, I plus 1, I minus 1, I. You see, okay, this is an inversion and this is an inversion.
So clearly we need to minimize the number of inversions in a way that such that ai plus I gets equal to bi plus I. Or I should say I is the original position and j is the final position of element ai. So we are minimizing the inversions of this permutation from I to j. Here I was thinking okay, how do I minimize inversions? Well, supposedly I have multiple values of I for which this value is the same, and then multiple values of j for which this value is the same. So probably I want to just pair them the smallest with the smallest, the next smallest with the next smallest, etc. And you can formally prove that that's optimal, but we are not going to do it right here, because I assume that's not very interesting. So yeah. Now the implementation time comes, and this is one of the tricks that you should know, just basically should know, if you want to solve it called a regular contest, I assume. And also it's quite common. It came up in Codeforces Global Round 16 this Sunday. Is you want to count inversions quickly. Well, in that round in global you actually did not have to do it quickly, but I kind of did quickly either way because I can. All right. And the way to do it in elegant time, with the smallest amount of code, I believe, is to use ordered set from policy-based data structures. So yeah. You can have a function count versions. I basically copy pasted that from global. So it adds elements one by one into ordered set, and ordered set allows you to find the order of each element. Yeah, so and then this is a number of inversions that this element has with previous elements. So each inversion we count when we come to the second element of this inversion, and we insert to just keep track of our prefix. So yeah, this was kind of an easy part for me, and I assume that you want to have some sort of this snippet somewhere in your library just to not code it from scratch, but it does not take too much time either way. It was I assume it would have taken 3 minutes maybe to find the block on Codeforces, copy paste all the stuff. This part I just know by now how to type it, so even if you don't have it in your library, it's not an awful lot of code to type. One more thing, you can of course do it with a Fenwick tree, which I believe is the preferred method on code interviews. So yeah. Just a side note, if you're preparing for an interview and you want to count inversions, then maybe you want to do it with a Fenwick tree. Or maybe you want to do it in merge sort fashion, alright? Well, when you merge sort, you can also count inversions. In case you did not know that, that's also an option. But I believe the Fenwick tree will be a second best after policy-based data structures, and merge sort will be the worst possible option to do that. No, the worst possible option is of course to count it naively in quadratic time, but still. Merge sort kind of takes more space to implement than I wanted to take. So yeah, but more interesting thing I think happens in the main part of the program, when we sort of I want to group indices based on this value, right? So I said okay, and I also want to have access to first and last. So normally I would put a set in here, but I realized that I actually process them in order, so I can use just a queue or a deck queue, because queue is just an adapter over the deck queue, so it just adds another level of interaction, which will probably be gone when compiler optimizes it, but whatever. I just prefer to use deck queue whenever I need a deck queue, queue or stack, just because it works faster, I think. And it's more uniform in a way. So yeah, so I have a queue, it's sorted. So then I come to like my vector b, I'm looking for this value. I know that I should take the smallest unprocessed and get rid of it. And this is like, this index is like what will be, which AI, which AJ I should say, will come to position I. So like A at this index gets to position I in the resultant array. And we just count inversions if it's possible, and if it's not possible, then we print -1. I'm not actually sure if you need this bit. I assume that you may need it, maybe not. So, like this kind of async returns long integer, and I believe that when you need like conditional operators, then this part and this part should have the same type, which may get tricky, like because of how well C++ casts values different ways. Like if you have a -1 here and then some character here, then character I assume will be casted to its integer representation, which may be very unpleasant. So yeah, it's a funny thing. Like I recently started programming in Rust, and I kind of did not. At first, I did not like how explicit it is about the types, but then I realized that C++ has just so much non-trivial type inference that I would rather specify the types myself, like, to make sure that it's the right thing. You have seen it previously with like LCM. Like if I did not put int64t there, then it will just compute the wrong result. So yeah, specifying types is better, I believe. Maybe someday I will try solving some problems in Rust, but maybe not, because I believe that you need like, for example, fast IO is not as trivial as here. You need some snippets in Rust to make it fast. So if you just do things naively, then it will not be that quick. So yeah. And as you can see, like this, this actually takes some time because of ordered set, I assume. Potentially also because of an ordered map into deck, yes, but I don't think that this is the reason. So yeah, just like a very common pattern, you want to know how to count inversions quickly, because that's going to be used. And then that is like just from implementation side. And from the solution side, you want to, often you're given like a construct configuration on which you can perform different operations. And sometimes the result does not depend on the order in which you do your operation. It kind of depends on the general way that things are like permuted or something like that. So you want to, whenever you can, you want to make such observations. They are likely to help you. Like if you notice that value of AI at first, like depends on how many positions it shifted either way, then you probably want to do that. All right, now we come to the last problem. Implementation side, it has like the most. It's very standard, but it just has more code than other problems that we've seen today. In this problem, we are given integers and m. We want to count the number of sequences A of length n, such that all elements are from 1 to m, and every successor is the multiplier of its predecessor. And of course, we need to do this modulo, because like, what else did you expect? The answer can be enormous, so it has to be modulo. So here I was thinking actually for quite a while, like, I don't know, maybe 20 minutes, which is kind of like a lot for a 500 points, but yeah. But it happens, it's okay, like, at least I'm solving problems because I like it, not just like blast past it. Potentially, like if you solve problems too quickly, then you practice on the wrong level and you should level up, I guess. Yeah, because the problems do get boring over time when you like see the same idea over and over again. So you want to evolve sometimes. So yeah. So in this problem, first thing I noticed, I started just actually filling up the. First thing that I thought of is dynamic programming for NM. My dynamic programming main idea was to count like how many sequences of each length end up with every element. And then for the next length, this is just like kind of sum of the previous layer over divisors of like AI should be a divisor of AI plus 1. But clearly that takes too much time. Next, I realized like what I realized and what helped me a lot is that the number of sequences that end at 2, end at 3, end at 5, and basically end at any prime number is the same number of sequences. Like, because like it does not depend on which prime you have, it basically depends on like on the fact that it's a prime. Next thing I noticed is that if you have numbers 6, 10, 15, and in general p times q, so the product of two different primes, and there is also the same number of sequences of some given length. Let's say there is the same number of sequences of length 4 that end with 6. That is the number of sequences that end with 10 of length 4. It's the same. So basically, at this point I thought, okay, so the number of sequences A of length n such that an is equal to n small only depends on the prime factorization of number n small. And not exactly on the factorization, like it does not even depend on the primes that you are having. It depends only on the vector of exponents that you have. At this point I realized, okay, there are not too many different ways or values of this vector, especially if you like, let's say, sort it. But I was thinking like, okay, that is actually still quite a lot. So I probably don't want to do that. So I should come up with some observation like how to compute the answer for every such vector quickly. So the main point so far was that the number of sequences of given length that end with a given element depends only the prime exponents in the factorization of this number. The next thing I realized is that it will be this function, there is some function, alright, that counts these sequences. Let's say that this count is f of n. And then what I say here is f of n is actually f of this vector of exponents. What I realized next is that this function is the product of some function of this function. Such product. Why? Because it kind of does not matter, like the prime divisors, the prime factors are often like orthogonal to each other, which you can see very clearly in such a picture that I like a lot. Let me draw it. So this is like a graph of divisors of number 12. And you can see like in this direction we have a division by 3, in this direction we have a division by 2. And this is what I mean when I say that prime factors are kind of orthogonal.
So what we have, we count a number of sequences that's just like go somehow from here to here, or maybe not from here to here, or from here to here. And notice that they can't stay like multiple times in the same place. That's okay. So why this holds is because like, suppose that you have sequence of steps like 1, 2, 3, 4, 5, 6, 7, right? It's a, like you can decompose vertical and horizontal movements. So if you decompose vertically, that will be like 1, 2, 3, 4, 5, 6, 7. And if you decompose horizontal, you will get 1, 2, 3, and 4, 5, 6, 7. And any two different inputs, different decompositions here and here will lead to a different decomposition overall. So that is one-to-one correspondence of product of these guys to these guys. And this is an idea I've seen not very often. That is more used in mathematics than in competitive programming. But yeah, sometimes if you have a function of like some just function on natural numbers, right? Positive non-negative integers. And it's kind of, it may be multiplicative, what I believe is what's called. It's just like it depends on the prime factorization. And then each prime is kind of separate. So that is more or less of an idea. Maybe not very often, but it's recurring, definitely. I've seen it already. At this point, we are basically faced like compute function of alpha I, of exponent. And after doing, I just did several experiments without much thinking. I realized that the answer will be binomial coefficient of n plus k over k Actually, I think it was like n plus k minus 1 by k. So n plus k minus 1 choose k is function of k. But then I realized that there's actually like normal way to come up with this. Is like if you're having this kind of thing, like here you want to compute function of 2, right? Because 4 is 2 squared. You want to come up with a decomposition. Decomposition consists of 2 lines, 2 bars, and then you have just your stars. Stars and bars is a very common way to visualize binomial coefficients. That was like the preferred way to coming up with this formula, not just by looking on values. But apparently I'm not very smart, so I just derived this formula from like small values. But yeah, of course, in general, you want to like have a formal proof which consists like, oh, okay, so like we have n steps, n minus n numbers, so n minus 1 steps, so that's like stars, and we have k bars, and therefore we get this binomial coefficient. That's kind of it for the solution section. For the implementation, like that is just a copy-pasted part. For modular powers and modular inverses, probably you want to have something like this. Or like, you can write it fairly quickly. I decided to go with like somewhat explicit names here for your convenience if you want to read this code. The links, of course, to all submissions will be down in the description as usual. So yeah, if you want to write them or to read them and maybe like implement the same thing yourself, then you're welcome to check the description. Binomial coefficients, I decided to pre-compute them. That was probably not necessary because each like maximum power that you can have is
20. So maybe that was not necessary, but I decided to pre-compute them. For this, I of course need the modular inverse, and I actually decided to chain pre-compute them. So each next binomial coefficient can be expressed as the previous binomial coefficient multiplied by this quantity. It was also not needed probably, but this way just less code actually. Then I have my sieve because I need to factor numbers, so PD is prime divisor. I believe it's largest prime divisor, or maybe not. Yeah, but it's definitely some prime divisor. And I have my function that returns my news, and it originates from the following notation, that a new base p of some number n is such k that p to the power k divides n, then p to the power k plus 1 does not divide n. So that's basically the exponent, so n is equal p1 new 1, etc. And probably we should write new p of n, new p1 of n, or new 1 for sure. So it's kind of different from the alphas i's that I used previously, but yeah. Sometimes I name the variables alpha, sometimes I name them new, that doesn't really matter. So yeah, this is another common thing that you want to have, that you can have your sieve and then you can factor quickly. And then I just compute the binomial coefficients, multiply a bunch of them, and this is I computed the number of sequences of length n that end at I plus 1. And I obviously have to add this up for all i's from 0 to m. So that is why I have this answer running sum. So yeah, quite several recurring ideas, but I quite like this the solution side. When you had to derive the formula, realize that it's independent of the prime factor that you have, that it only depends on prime exponents, and then it is multiplicative in prime exponents. It was also quite nice. Also a little bit of combinatorics at the very end. So yeah, keep in mind again, these problems are underrated, I believe, but by at least 200 points. So yeah, that is definitely expert level. Because all of these tricks, they don't appear very often at beginner level competitions. Maybe that's why these problems are for A or C, but then they are not so hard. Not so hard for A or C participants, because the tricks are indeed quite common. So basically it's most of the, in ABCs, some substantial part of difficulty of rating of the problem comes from the implementation side, because a lot of ABC participants have difficulties with implementation, which I believe is not about you, because you follow this channel, you see the recurrent ideas, and therefore hopefully you don't have problems with implementing them when you see them. Like you've seen it implemented, hopefully you upsolve the problem yourself as well, so you have the corresponding snippet. And if you ever see the same idea again, you'll be ready for it. Yeah, but a lot of ABC participants don't follow this channel, so therefore they face difficulties with implementation, which is not the case for A or C participants, because they are more experienced. They know these patterns. They know how to implement this. So majority of difficulty of A or C problems comes from the actual solving part, which is so therefore I believe they are a bit underrated when compared to ABC problems. That's it. So yeah, that's kind of all I wanted to share with you today. Tomorrow we'll be back with even harder problems from ARCs. This is all a part of my sort of preparation for the upcoming ARCs. I hope it will go reasonably well, but we'll see. Like, this is something I haven't done in quite a while, like 4 months, maybe more. So yeah, definitely, like, it may be tricky to get back into the things. But we have not one but 2 upcoming ARCs, so I hope that at least the second one will go well. So yeah, thanks everybody for watching. I hope you learned something new, and I'll see you tomorrow. Bye bye.